Welcome to lecture 11 of the course on high performance computing. Today we are actually moving into a new set of topics, a new kind of discussion. Until now, as you look at the agenda on the slide, you'll notice that until now we were talking either in general terms about programs, or we were talking in specific terms about the hardware. And those were the two items in the beginning of the agenda for this course, which are listed 1 and 2. And from today on, for the next 10 lectures or so, we're going to look at some of the software which is on a system to help in the execution of the programs that we run. So that's the agenda for the medium-term future. So just to recap, hitherto we've been looking at the computer at this level, and we've pretty much understood the components of each of these building blocks. We know a lot about the main memory. We've seen how important the registers are. We haven't actually looked at the design of arithmetic or logical functional units, but that's not really that important to us as people who are primarily interested in learning what happens when our programs execute on a computer from the perspective of trying to make them more efficient or faster. In the previous lecture, we looked a little bit at how the control hardware manages the execution of instructions. We talked about the different special purpose registers that might be present and how they might be used by certain logic circuitry to achieve the execution of instructions. We also have an approximate idea about what the memory management unit does, and we understand that without the presence of this cache memory, the amount of time to execute a single instruction might be very large due to the wide speed disparity between the main memory and the processor. So with this general, but in fact somewhat specific understanding of how the hardware is organized, we can now move into the software. We can start looking a little bit at what's happening on the software side. And I'm going to continue to use the term computer organization because we're going to look at certain aspects of the software other than the programs that you write. There are, as you may be aware, several components of software which are sort of permanently available on computer systems. Your programs come and go, but there are certain components of software which are always there and are integral parts of the computer system. Hence, I will continue to use the word computer organization, since these pieces of software are an integral part of the computer system. Now, in the previous lecture, when I raised the idea that we have an idea what the hardware is like, but there could be more than one program running at a time, or concurrently. I use the term concurrently. So what this told us is that we must expect that the hardware resources of the computer system that we have seen in the computer organization hardware slide are actually shared by those programs in execution. There could be 5 programs in execution. So there must be some software which is helping in doing this, and one of the very special pieces of software that manages or helps in managing the sharing of the hardware resources among the many programs in execution is known as the operating system. So we do need to know a good deal about the operating system to understand what happens when our programs run on a computer system. So let's just look a little bit at operating systems. So the operating systems is typically abbreviated as OS, operating system. And in your experience with using computers, you will have encountered, I'm sure, many different operating systems, or would have come across literature where many different operating systems are mentioned. Today, one of the more prominent operating system names that you may come across is Unix. Unix is the name of a family of operating systems which has been around for about 40 years now. It's been around for a long time. It has its roots in some design activity at AT&T Bell Labs, followed up by some design activity at some universities, both in Europe and in the US. And today, if you look into the term Unix, you'll actually find out that there are many variants of Unix. I'm just giving you a few examples of variants of Unix from the not too distant past. So for example, there's a variant or a kind of Unix called AIX, and AIX is in fact was the IBM version of Unix. It was the version of Unix that you would use if you wanted to run a Unix operating system on hardware that had been built by IBM, the company IBM. Similarly, there is an operating system called HP-UX, which, as you would imagine, was the HP, Hewlett-Packard operating system. So on their hardware, they would typically run HP-UX operating systems. And then there is Solaris, which is and was the Sun operating system. So clearly Unix is not a specific operating system. The term is used to refer to a family of operating systems, and the elements of the family could be hardware specific, as we see in this example. AIX meant for IBM hardware using IBM processors. HP UX meant for Hewlett-Packard systems using particular Hewlett-Packard design processors. Solaris used to run only on Sun hardware, but has been modified so that it can run on any of the Intel processors as well. So all of these have something in common, and that's why they're all called Unix, and therefore there is some standard properties of a Unix operating system. And there could be some other variants which do not comply entirely with those standards and might be called Unix-like in some cases, since they have a general look and feel of Unix. Now another term or name of an operating system that you may have come across is Linux. Linux has become very widespread. I imagine that many of you have Linux running on your laptop or desktop at home, certainly in your labs at school. I'm sure there may be Linux machines. The property of Linux is that unlike Unix of the upper line, like AIX or HP UX or Solaris, which you typically bought from the company, Linux is actually available in a form called free software. It's not only is it free software, but it's open source. So the source code, the actual C programs which form the implementation of the Linux kernel or the Linux core operating system are actually freely available. One can download them. However, just having the kernel in source form is not very useful to you or to me, since what we want is an operating system which can run on our let's say our personal computer and help in the sharing of the resources of that personal computer, and we don't need to know what the source code, the C programs that are doing that look like. So we are more interested in getting some kind of a distribution which might include the Linux kernel along with other programs of interest to us, such as maybe compilers or development environments, etc. So you will have possibly come across many distributions of Linux. For example, you may have heard of Fedora or Red Hat Linux, OpenSUSE, Ubuntu or Debian. So these are all just not variants of Linux. All of them will have the Linux kernel. There's only one Linux kernel at any given point in time. Of course, there could be copies of older Linux kernels, but there's one most recent version of Linux which would be the current Linux kernel. And one could get it in any one of the distributions that are listed here. Now, there are others as well. The world is not just Unix and Linux. For example, if you have a Macintosh, an Apple computer of iMac or something like that, then you will be aware that the operating system on those computers is the Apple Mac OS, which was originally developed on certain Unix-like from a Unix-like base called Mac. And the current version of the Apple Mac OS, which you have on your own computer, is called the Mac OS X Snow Leopard. The previous one was called the OS X Leopard, I believe. So that is subtly different from either of the Unix or the Linux. Once again, this is an operating system that one buys or one gets on an Apple machine when one purchases the Apple machine. And that is not the end of the list of operating system examples. If you have a Windows machine, then you should be aware that the operating system there is what is known as Microsoft Windows, and there have been many developments in the Microsoft Windows operating systems. Today you have Windows 7, previously there was Windows Vista, before that Windows XP, and a line of Windows operating systems prior to this. So these are all developed and sold by Microsoft, and they're all operating systems, quite different from the Unix or Linux or the Apple Mac OS. Now in more recent times you may have heard of the Google Chrome operating system, which under development by Google, and this is primarily intended for web applications. It's not meant to manage hardware in the sense that the others are, and is once again based on a Linux-like kernel, a Linux kernel, I believe. So there are many operating systems, and it is now not our objective to learn something about each of these. What we are actually going to do is to try to talk about operating systems in an abstract Unix-like sense. So we will talk about things from the perspective of, since all of the examples that we have here, for the most part, are Unix-like, we will use that perspective in our discussion of operating systems. Okay, now we're talking about the software side of the core components of a computer system, and the operating system seems to be an integral part of that. But there are other concepts that we must be comfortable with before we can understand what happens when our program executes. And one of the fundamental concepts is the concept of a process. And basically the process is not a piece of software. The process is an abstract entity, and we'll think of it as being a program in execution. So henceforth, rather than referring to my program in execution on a computer system, I could talk about the process, which is the execution of my program on the computer system. And the process is at this point, as far as from what I'm telling you, an abstract entity which represents the execution of the program, of your program on the computer system. Clearly it is not, it must have an implementation, otherwise it could not cause the execution of instructions. Therefore it's a concrete entity as far as the software side of the computer system is concerned. And we'll talk more about that a little bit later. So we will use this term, process, from now on, instead of talking about a program in execution. And shortly we will see that this is not actually a very good, this is not a definition, this is just, the term process does not mean program in execution. But for the moment we'll just use it in this sense and get a finer understanding as the next 3 or 4 lectures. Okay, now what it means for a program to be in execution, as we have seen, is that that program must be present in the main memory of the computer system, and it is in a state where its instructions are being fetched from main memory into the processor and executed based on the hardware's understanding of what those instructions mean. So that's what it means for a program to be in execution. And we've seen that there could be more than one program in execution concurrently. In other words, more than one program present in main memory, and the instructions of these multiple programs are somehow fetched into the processor and executed, and that's something we have to learn more about. But we can get some practical understanding of the fact that there could be more than one program in execution on a computer system at a time, or specifically on a Unix system, because there is a mechanism available. In other words, this thing which I now call PS, which in fact stands for process status, which can give you information about the status of the processes which are currently on the computer system. Right? Now, so you could actually use PS. If you're logged onto a Unix computer system, then you could type PS as a command and be given. You'd expect that in return you would get a lot of information about the current status of the processes which are on that computer system. In other words, the programs in execution on that computer system. Now in this notation that I've used here, I've used this before. Remember that that % sign which I'm showing on the left is what I call the shell prompt. I never actually told you what the shell prompt was, but the impression that you have is that when you're logged into a computer system in this particular mode, a Unix-like computer system, then you will see a % sign or something like that on the screen. In general, that thing which you see on the screen is called the shell prompt. It is prompting you to type something in, a command in. In this particular instance, I have typed PS because that's the command which I want to execute. I want to get information about the current status of the different processes. And on different Unix systems, you may find out that the shell prompt is different. Right? In some Unix systems, the shell prompt might be a $sign. In others, somebody may have configured it so that it has more information in it. But in any event, there's some string of characters which prompts the user to type something in, and that is what I mean by the shell prompt. And in my examples, I will use the % as the shell prompt. So we understand where the word prompt is coming from, because the purpose of that % appearing on the screen is to prompt the user, in other words, to request the user to type a command in. We do have to understand what the first term is. What is the shell? So let me tell you that the shell, the word shell, is used for a command interpreter, and it is through a command interpreter or a shell that you interact with the Unix computer system. The command interpreter or the shell asks you for a command through the shell prompt. You type a command in, and then the shell takes the command and interprets it. In other words, it does whatever has to be done to achieve the command that you have typed in. Okay, so we primarily in this mode think about interacting with the computer system, the hardware and the software, through the shell, which raises the question of what is this shell? It is possible that the shell is a special piece of hardware. It is possible that the shell is just a part of the operating system. The third possibility is that the shell is just an ordinary program. And it is in fact what we are going to find out. On Unix systems, even on Linux systems, you will find out that there are many different shells available. For example, there is a shell called the C shell. There is another shell called the BA shell or bash. And you could actually choose on a Unix system to use any shell among those which are provided or which are available on that computer system. It's a user choice. Right now, to answer the previous question that I had raised about whether the shell is a piece of hardware or part of the operating system or just a program, the answer is that the shell is a program. It's just another program. The reason that I stress this as just another program is because if I were to say that the shell is a program, that would not demystify the question of whether the shell is an important program like the operating system. The operating system too, for the most part, is just a program, sorry. But the shell is just a program in that it is just a program like the a.out which you generated by writing a program.c. You could write your own shell. You could write a shell.c program which does a command interpretation. You could compile it into an a.out, and then that a.out could be your shell. In that sense, shell is just another program, and we'll understand specifically what a shell does shortly. So the operating system is a very important piece of software. When a program is in execution, it exists in the computer system as something which we'll call a process. The program itself is a piece of software. The process is the execution of that piece of software. Then we interact with the computer system through a shell, command interpreter, in the case of Unix systems. And two examples of shells are CSH and BASH. Now, on the previous slide, I had mentioned that in response to the shell prompt, if I had typed the command ps, then I could get information about the different processes in execution on a computer system. So let's just try that. Let's suppose that I'm logged into a Unix system and I type ps, and then I hit return. I'll get an output from the system that might look something like this. So there's a lot of information which is output, and remember that the purpose of this command was to give me information about the status of processes on the system. So since there are two lines of output that I receive, I suspect that I have at least two programs in execution. And that's what I see. I notice that there are two lines, and one of them, strangely enough, is an indication that the command which I had typed in is one of the programs in execution, but that should not be too surprising, because when I type the ps command, if ps is the name of a program, then the program has to execute. And while it is executing, it is causing these lines of output to be printed out. And since while it is executing, it is a program in execution or a process, there will be a line in the ps output corresponding to itself. The other line in the ps output is also interesting because we've come across this name bash before, on the previous slide in fact, where I had mentioned that I gave you two examples of command interpreters in Unix. One was CSH and the other was bash. And we see that bash itself is listed. So there's a process which is the execution of the command bash. So bash 2 is just a program, an a.out which has been renamed as bash, and it is executed, and it is the execution of this program which is creating the prompt on the screen, reading in whatever I type in, and causing the different instructions in the bash program are what are causing the execution of the ps to happen, ps program to happen. So you clearly see that bash is not that complicated, and shortly we'll see how you could write your own simple shell. Now from this, it looks like the ps program is capable of giving us information about the important processes on the system. And in the system at which I typed this command, there were these two important processes running. But this is not the whole story. If you actually read more about ps, you'll find out that ps can be executed with different command options. For example, if I type ps with the command line option -a, this is a specific request for information about all the processes which are executing on the computer system. So the previous listing was clearly not of all the processes, but of some subset of the processes. So if I now type ps -a, what I get is a larger listing. So this is the same system on which I had got two lines by just typing ps. By typing ps -a, I get an output from this particular program called ps, which has 6 lines in its output. Right? So clearly there are more processes, there are more programs in execution on the system than just BASH and PS at this point in time. And again, if you look at the output, you'll notice that one of the columns in this output of PS is the TTY, and it was present in the first also. Previously, when I typed PS, if I looked at the TTY column, I noticed that you can read TTY as terminal. TTY stands for terminal, essentially saying that from the terminal number 10, in some sense, these two commands had been executed. What I am getting in the PS minus A listing is information about what is happening from other terminals as well, conceivably other users or something of that kind. So it looks like there are at least 3 other terminals active, and some activity being initiated from each of those terminals, programs in execution from those terminals as well. So from PS minus A, I get more information. PS seemed to be giving me information just about the particular terminal at which I was sitting, or the particular processes, information about the processes in connection with me, whereas PS minus A is giving a broader perspective of what is happening on that computer system, programs in execution due to possibly other users. And there is another possibility. I could actually type in PS minus L, and this is asking for a long listing, which will give a lot more information. For example, when I type PS minus L, I get information about a long listing about the processes associated with me, and there are many more fields. Right? In addition, in the previous listing, I had the PID, and I had the TTY, and I had the time, and I had the command, but none of these fields, which now give me a lot more information about the status of the process, of the different processes. And we'll see more about what these fields mean as we understand more about what it means to be a process, or what happens when a program is in execution on a Unix-like system as a process. Okay, now moving ahead, we've seen that from the perspective of the hardware, this is what the computer system organization looks like. Our objective is to understand the relationship between the operating system, which is the most important piece of software in some sense, the processes, which are all the programs in execution on the computer system, and the hardware. So the diagram that we have on the screen is the hardware, and we want to understand the relationship between this and the rest of the important components, the rest of the software organization of the computer system. So I'm going to shrink this particular box down in size. It's no longer as important. We don't need to know the details. We don't need to discuss the details of the individual components of the hardware anymore. So I'll shrink it down in size to about this big and leave the rest of the screen for our discussion about the software side of the organization of the computer system. And since we're not particularly interested in the building blocks of the hardware anymore, we know something about it, I'll just abstract it out as a box labeled hardware. So remember, when you see the box labeled hardware, it has that CPU, memory, hardware, bus, I/O devices, and so on. So what else is there in the computer system? Now, we understood that the operating system is the piece of software which manages the sharing of the resources, including the hardware resources of the computer system. So we expect that there must be some, and we also understood that there are many programs in execution on the hardware. So there will be, I'll represent the different programs in execution or the different processes by these circles which you see up towards the top. They're different colored circles. I'll mention why shortly. So in this particular example, there seem to be about 11 processes sharing this particular piece of hardware, 11 programs in execution. Now we saw that the actual sharing of the hardware resources was going to be managed by the operating system. So the operating system must enter this picture. I'll show a box labeled operating system over here. The reason that I show it between the processes and the hardware is because the hardware resources, the sharing of the hardware resources among the processes is managed by the operating system. So in some sense, the operating system is an intermediary between the processes, programs in execution, and the hardware. Therefore, I show the operating system in between the processes and the hardware. Now, whenever one of the processes wants to do something with specific part of the hardware, for example, let's suppose one of the processes wants to read from a file. The file is one of the the file is possibly associated with one of the I/O devices of the hardware. It's somewhere down here. So if one of the processes wants to do something on a file, it must clearly get help from the operating system to do that. And the way the operating system is structured is that there's a collection of things called system calls which are what the processes are going to call in order to get the functionality required as far as the shared hardware resources are concerned. Therefore, the process which wanted to do something to a file would call the appropriate system call, and through that it would actually be able to access the file or do whatever it wanted to do. So the system calls are an important aspect of the operating system. Now, instead of referring to the other odd shaped box as operating system anymore, I am going to refer to it as the operating system kernel, since it is not the entire operating system. The system calls are also in some sense part of the operating system. The operating system kernel, as the name suggests, is the central, integral, important core content of the operating system. Some of the functionality of the operating system may be implemented elsewhere. For example, some of these processes that you see over here are yellow operating systems, and you would have noticed that the color yellow in this slide is being used for operating system components. So what is being suggested is that some of the processes, in other words, some of the programs in execution are actually operating system processes. They are doing something for or on behalf of or as part of the operating system. Therefore, the operating system should not be viewed as a single program, a single piece of software. It's many pieces of software. There is this core component, the core or kernel part of the operating system, which is called the OS kernel. They are the system calls through which functionality is made available to the processes. There are also some processes, some programs in execution which are really operating system related, and that's why they are all colored in yellow. The other white processes are just programs in execution of ordinary users like you or me. Ordinary programs in execution or ordinary processes. So the first thing to note is that the system calls are an important thing for us to know about, because it is through the system calls that a process of mine, in other words a program of mine in execution, will be able to get some kind of functionality out of the operating system. So we do need to know a good bit about system calls, and we'll spend some time doing just that. So as I said, the system calls or a system call is how a process gets the operating system to do something for it. Right? So you get functionality out of the operating system or the operating system kernel by making a system call. And in that sense, you could view the collection of system calls as an interface for interaction with the operating system. The only way that process can interact with the operating system to get functionality is using the system calls. Right? So there's this collection, small number of system calls. In a typical Linux or Unix scenario, the number of system calls is going to be a few hundred, 200 or 300. I forget exactly how much. So in that sense, I refer to it as an interface. It's a collection of functions in some sense that one could call. It's a specification of the mechanism for interaction between the process and the operating system, the OS kernel. Often in reference to software systems, people will use the term API, which expands into application programming interface, as to indicate that it is a specification. An API is a specification of how a piece of software can interact with another piece of software. In this particular case, the system calls are a specification. They tell you exactly what, exactly what information you must provide and with what details in order to interact with the operating system. In that sense, it is an interface. So there are going to be many different system calls for the different kinds of functionality that a process may need to get from the operating system. So let's look at some of the system calls. So in some Unix systems, you will find out that the operations on files are provided, or functionality as far as operations on files are provided through system calls. I believe you will all be aware with files. For example, when you have a program which needs to maintain data well beyond the lifetime of the program itself, then your only option is to store the data in a file. It's basically a mechanism through which information can be saved for long durations of time. Remember, when your program executes, it may have variables in memory, but they cease to exist when the program finishes execution. The largest lifetime of a piece of data was the execution time of a program. Therefore, if you want data to exist beyond the lifetime of a program, one basically has to be using files. And many of you will have written programs that deal with files. So there's a permanent form of storage. One can read, write, various other operations on files. So the list of operations which I'm going to put up next will not be too surprising to many of you. And we expect that there are system calls for doing these operations. So first there is a system call using which you can create a new file. The system call in many Unix systems is called CREAT. So it can be used to create a new file. The new file once created will be empty. One may want to add information into the file. The protocol that is used in operating on a file is in Unix-like systems is that one must first formally open the file. So there is a system call through which one can open the file, and by opening the file one is essentially saying making it possible for subsequent reading or writing of the file to take place. Now I had listed a system call before that called unlink, and the unlink is the system call which is provided when one desires to remove a file. So after when you are sure that the file is no longer going to be necessary for other programs or for this particular program, one could use unlink to possibly remove the file. So as I said, the protocol for using files is that one must first, for an existing file, one must first open the file using open, and one can subsequently read from the file. So there's a read system call using which one can read data from an open file into a variable. Remember that read is going to be used essentially by a process, and the objective of getting data from a file is going to be to operate on it within a program, the program in execution, and therefore it must be available in a variable. So read will read data from a file into memory locations, main memory locations, which is what we refer to by a variable. Similarly, if one wants to add data into a file, one can do so using the write system call to write data into an already open file. Right? So one could add additional information into a file using write, or one could overwrite information in the file using write. There is a system call relating to changing the current pointer into the open file. Note that when I'm reading from a file, I may want to read from the end of the file, in which case I could use lseek to change the current pointer into the open file and then read from the end of the file. And with this, there are other possible system calls related to files, but this is a representative set. Now many of you, when you wrote your C programs, would have used open, read, write, and lseek, and possibly create. You should be aware that the function which you call to do this within the C program was not the system call directly, but essentially a function inside a file I/O library of some kind, and that function would actually make the system call on your behalf. Right? So even though you did use functions called open, read, write, and lseek, you were not directly calling or making the system call, but were calling a function which was going to make the system call on your behalf. This is just to clarify that you have used these names before, but you have not actually used these system calls directly from your C program. So we've seen that there are many kinds of functionality which the operating system can provide relating to requirements that a program in execution may have relating to files, operations on files. Now there could also be operations or functionality that a program in execution will need to operate on processes. This is an interesting idea. Remember, the system call is going to be called by a process, and a process may have to operate on itself or on other processes. So this is a new kind of a concept. Possibly none of you have written programs which use these system calls before. But by looking at the first example, we understand why this might be useful. The first system call that I've listed is a system call called fork, and it can be used to create a new process. So what this essentially means is I could write a C program. Within that C program, I could use the fork system call, and the effect is going to be to create a new process. And in fact, I could have a program which has multiple calls to fork. I could write a program which calls fork 5 times, and the net effect is going to be that that program is going to execute as one process, which was its original, the process which came into existence when I asked that program to be executed, and then 5 additional processes due to the 5 forks that may have taken place. So the program would ultimately run possibly as 6 processes. And this is the reason that I mentioned earlier that it's not entirely fair to say that a process is a program in execution, because the particular example that I just described, there are 6 processes which represent the program in execution. No one of the processes fully represents that program in execution. Okay, so fork is clearly going to be interesting. Now the terminology which we use in reference to fork is, remember that if there is a process which calls fork, the net effect is going to be that a new process is going to come into existence, which means that I will then have two processes representing that program in execution, and I do therefore need to have some terminology to distinguish between them. So the standard terminology used is to use the term parent process to refer to the process that did or called fork, and child process for the process that came into existence as the result of the execution of fork. So in this particular example, the parent process calls fork, which is a request to the operating system to create a new process, and the new process which comes into existence is the child process. So a single parent process can have multiple child processes. Any child process will have only one parent process, which is the process that caused it to come into existence. So fork is an important system call. Now one of the things which you will learn about fork is, after the fork is done, there are two processes in execution as far as my program is concerned. And we are now, if you look at the next point which I have put, both the parent and the child processes continue to execute from that point in the program. And what I mean by that point in the program is the call to fork. And we'll look at this in the next slide, the ramifications of this idea. But this is the bare essentials as far as fork is concerned. Fork is a system call that can be used to create a new process, and the effect is a child process comes into existence, and both the parent and the child continue execution from the point of the return from the fork, the call to fork. Now another important system call related to processes is the exec system call. And in brief, the description is that exec is used to change the memory image of a process. Now this might be useful, for example, to change the program that a process is executing. And we'll see how this works shortly. But this is one of the possible uses of the exec system call, to change the program that a process is executing. An odd concept. Now let's think about this. Let's put fork and exec together in this one example. Let's suppose that I have a parent process in execution. So representing that I have a program in execution, and it is represented by a process which I will for the moment refer to as the parent process, since this parent process is shortly going to do a fork. Okay, now this process is represented in memory by things in memory that relate to it. For example, we saw that associated with any program in execution, there is its program, which we call the text. There is its statically allocated data, its heap allocated data, and its stack allocated data. And both the stack and the heap can grow and shrink as the program executes. The data is of fixed size since it is statically allocated, and the text, the instructions of the program, typically do not change when the program is in execution. So when I talk about the memory image of a process, this is what I am referring to. This is the memory image of the parent process. Okay, so when the parent process is in execution, the parent process could do a fork. And when a process does a fork, as we saw, the effect is that a new process comes into existence. This new process is called the child process. It turns out that the child process starts off identical to the parent process in all except one or two subtle points. We just learned from the previous slide that after the fork is done, I have two processes, the parent and the child, and both continue execution from the point at which the fork returns. So let's just look at a code example. So at this point, from what I've told you, the child process starts off with the same text as the parent, the same data as the parent, the same heap as the parent, and the same stack as the parent. It's basically identical to the parent as far as its memory image is concerned. Now, how do I actually set this up? Let's look at a C program in which I'm calling fork and exec. So the yellow object on the right is some extract from my C program. So the way that I call fork is by calling fork as a function in this way. Once again, when I use fork in this form inside a C program, it is conceivable that I'm not actually making the system call directly, but I'm calling a function called fork which will make the system call on my behalf. Now, if you read details about fork, you will find out that fork has a return value. And therefore, when I call fork, I call it with an assignment, and I remember the return value from fork in the variable called retval. Retval is an integer. So the integer variable retval. Now, in what follows from what I just described, you understand that both the parent process and the child process are going to continue execution from this point in the program. In other words, the point at which return has been transferred back to my program from the fork system call. So both the parent and the child are going to be executing at this point in the program with basically the same, practically the same memory image. They, however, do differ in one or two subtle ways, and one of the subtle ways in which they return is in the variable retval. So if you look at the details about the fork system call, you'll notice that the parent and the child will differ in their value as far as the variable return val is concerned. Therefore, after return from the function from the system call, if my program is written so that the first thing that it does is it checks retval, the value returned by the fork system call, then I can actually distinguish between the child, which will have a retval of 0, and the parent, which will have a retval which is not 0. And therefore I can cause the parent and the child to start doing different things. It is not always useful to have the parent and the child returning and both doing exactly the same thing, because it may be useful for me to divide the functionality of the rest of my program across the parent and the child, rather than causing both of them to do exactly the same thing. And I could therefore achieve it by writing my program to have different operations for the parent and the child after return from the fork system call. One thing I could, for example, do is to call the child to do something substantially different by actually making a call to exec. Remember that the exec system call is used to change the memory image of the process which essentially calls it. In this case, the child process is calling exec, the parent process is not. And therefore, what's going to happen is that the memory image of the child process can be caused to change. Now, I'm not showing you the parameters to exec, but as you'd imagine, one of the parameters to exec is going to be the identity of a program which could be executed. And then what will in effect happen is that the new program which I have listed, which I've mentioned over here, is going to become the program that the child process is executing. So that is going to cause the text and the data and the stack of the child process to change. So you notice that after the exec, the text of the parent and the text of the child are completely different, because the child process is now running a different program, and therefore its statically allocated data is different, and its stack is going to be different, and it won't have the same heap as the parent process anymore. Therefore, the child and the parent processes are now different from each other, and that was achieved by this call to exec. Right? So we see that both fork and exec are important operations on processes. Fork is an operation on processes in that it can be used by one process to create another process, and that's why I might include it in a program that I write, so that when the program is in execution, the process which is that program in execution will fork and have a child process. And exec is useful for a process to modify its memory image. Exec actually has it's a family of calls, and you would need to read a little bit about this before using it safely. Okay, so much for fork and exec. These are, as I said, examples of operations on processes. We are talking about system calls. These are two examples of the system calls that are provided by Unix-like operating systems for operating on processes. I'm going to mention, I think, just one or two more. There is a system call called exit, and this can be used by a process to gracefully terminate. Right? And what it means to gracefully terminate is that the process which calls exit will cleanly terminate. There will not be any uncertainties about the state of it or its of the computer system as a whole when a process terminates, if it is terminating using exit. And even if you don't explicitly call exit or cause a wrapper function, even if you write programs which don't explicitly contain exit inside the code, inside the program, you can understand that it might be implicitly called for you at the end of the main function or at the point at which your program normally terminates. This is something that the compiler could quite easily insert into the a.out. In other words, a call to the system call exit in order to cause a graceful termination of your program. One other system call I'll mention is the wait system call. And the wait system call relates to the relationship between a parent process and its child. If the situation is that you want the parent process to do nothing but maintain its current state, in other words, to sleep until the child terminates, then you could use the wait system call within the parent for that purpose. Right? So this allows one to cause some kind of synchronization between the activity of the parent process and the activity of the child process. Right? So the parent process, while executing the wait, in executing the wait system call, is essentially saying that it would like to stay as it is until the particular child process has completed whatever it was supposed to do, whatever it was created to do. So there are several other instances of system calls for operations on processes, but this representative set of 4 will give us some idea of the nature of the functionality. Finally, I'm just going to talk about the possibility of there being system calls for operations on memory. You'll remember that until now we talked about main memory, and we know that there's text, data, stack and heap. We know that there could be multiple programs in execution at the same time, in which case there could be multiple text, data, stacks and heaps. In other words, multiple memory images, one for each process in the memory at the same time. But when I talk about operations on memory, I'm talking about something relating to specific operations that a single process might request of the operating system. And I'll give you one example of a system call in this area, and that is the system call known as SBRK or SBreak or setBreak. And from our perspective, to understand what a system call like setBreak might be useful for, let me just mention that it might be useful to me if I was implementing a memory allocation library, a dynamic memory allocation library. Now, when we talked about the memory image, we talked about the heap and the stack as both growing. So the heap may have to grow as more and more dynamic variables are allocated, and it might shrink as more and more dynamic variables are freed. The stack has to grow as more and more function calls are made, and it has to shrink as the function returns are executed. We know how the growth and shrinkage of the stack happens. That happens explicitly because of the stack operations that are generated by the compiler in connection with function calls and returns. But I didn't say anything about the growth and shrinkage of the heap. Now, as it happens, the growth and shrinkage of the heap is managed by the memory allocation library, and not in most cases along the lines of how the stack growth and shrinkage are managed. Rather, every once in a while, the memory allocation library will request the operating system to increase the size of its allocation. In other words, let me just go back to the slide where we had that memory image. In other words, if there's a need for growth of the heap, then the memory allocation routine would call SBreak, and the result of SBreak would be that there would be an increase in the size of the heap. The heap would now be this big rather than how big it was before. So it has something to do with increasing the size of data associated with this region of memory, which is why for the first time I'm showing the heap. Until now, whenever I showed text, data, stack and heap, I was showing you text, data, stack growing downwards, in other words, stack growing to higher and higher memory addresses, and heap growing to lower and lower memory addresses. This is the first time where I'm showing you heap growing to higher and higher memory addresses and stack growing to lower and lower memory addresses. And it is primarily for this purpose, that it is conceivable that the heap growth is dictated or managed by calls to SBreak. SBreak is a system call which is a memory related system call, and could be used by a memory allocation library to increase the size of the heap. There could be again other, but this is the one which we can sort of understand at this point in time. In short then, there are many different system calls which are basically interface mechanisms which are available for use by any process for getting functionality out of the operating system. And you could write programs, as we saw, using these system calls. We saw a program which used fork and exec. We've seen that the memory allocation library might use SBreak, and so on. Okay, so we've seen many examples of system calls. Now, one key observation which I will make at this point is that from our diagram of the computer organization software, we understood that the system calls were in yellow. The code of the system calls, the instructions associated with the system calls, should be viewed as being part of the operating system. Therefore, when a process calls a system call or executes in a system call, bear in mind that it is actually executing operating system code. Right? the diagram that we had was of that yellow operating system blob with those yellow system call rectangles sticking out at the top. So when a process calls a system call, it is executing that yellow code inside that yellow system call block. It is executing operating system code. Right? So when this process calls this system call, it actually starts executing the instructions in that system call. Right? That is something we have to bear in mind. Now, from the time I introduced the term operating system, I have been careful to say that the operating system is a very special program. It's not an ordinary program, like a program that you or I could write, because the operating system does very special things. It interfaces between the processes and the hardware. It manages the sharing of the hardware among the different processes, and therefore it is capable of controlling, managing, manipulating the hardware. Therefore it is special. And in order to do the sharing of the hardware resources, the operating system code must have special privileges. It must be able to do things that ordinary programs that you or I write cannot do. So when a process executes in a system call, it is temporarily very special. The process is executing the yellow instructions inside the system call, and the yellow instructions inside the system call may be doing very special operations, very privileged operations, since they are part of the operating system. Therefore, when a process of yours, when a program that you write a program which calls fork, when your process is executing fork, it is actually executing those yellow, very privileged instructions. So a process must be allowed to do sensitive operations when it is executing in a system call. And therefore, the entry into a system call is a very critical juncture in the execution, during the execution of your program. When your program enters a system call, starts executing a system call, suddenly it is doing things which might be very privileged, and therefore this has to be controlled very carefully. And therefore, in any instruction set architecture, special instructions will be included for this transition, the transition between your process doing ordinary things, which are entirely entitled to do, and your process actually entering a system call, and therefore suddenly having to do very sensitive things. Okay, now in the operating system, the instructions must be provided for it to do the privileged operations, and these are called privileged instructions. And we have not seen any of the privileged instructions of the MIPS-1 instruction set, because we will not see them in the programs that we write, and we are not going to write since we are not going to write an operating system. But if you actually looked at operating system code, like the Linux binaries or something like that, you may actually see the privileged instructions. Okay, so the privileged instructions are included in an instruction set for use by special programs like the OS. The operating system kernel will use many of the privileged instructions. Some of the operating system processes, the yellow circles at the top of our diagram, may also have to use some of the privileged instructions to do the special things that they do. And therefore, we do need to understand the transition, which I had talked about over here, much more carefully, in much more detail, before we can see that the operating system is in fact this very special entity which is being protected, and why this protection may have to take place. So I'll stop here for today, reminding you that in today's lecture number 11, we have started looking at the organization of a computer system from the perspective of not just the hardware, but from the perspective of the software that executes on the hardware. And we've understood that a very special piece of the software is the operating system, and that the key functionality of the operating system is present in something called the operating system kernel. The different programs in execution, and there could be more than one on a particular computer system, is each represented by at least one process. Process is a program in execution. Some programs in execution will be represented by more than one process due to the fact that they may explicitly create more processes through special requests to the operating system. In general, special requests from a process to the operating system are achieved through what are called system calls. The collection of system calls is the interface between the ordinary user program and the operating system. Thank you.